Hello my dear students, welcome back to the session. Here we're going to see network theory subject we are already in, and we finished 3 chapters successfully, that DC circuits, AC circuits, transient analysis, isn't it? Now today we're going to see the 4th chapter, magnetic coupled circuits. In this magnetic coupled circuits, now let us see here. We start with the circuits classification. How do you classify the circuits here? The circuits are classified into electrically coupled but magnetically separated. Separated or isolated. Okay, so people call it conductively coupled otherwise. Conductively coupled but inductively separated or isolated. Okay. The second type of circuit is magnetically coupled but electrically separated or isolated. Okay, so magnetically is nothing but what? Inductively coupled. Electrically is nothing but what? Conductively. Okay, so conductively separated or isolated. The third type of circuits are both electrically and magnetically coupled. Understand all of you? 3 types of circuits we can see. Okay, so best example for a magnetic coupled circuits which we use in our day-to-day life, that is transformer. Okay, transformer. So it has primary winding, secondary winding. Okay, let me draw it. Primary winding and secondary winding. A non-magnetic core, isn't it? A non-magnetic core it is. And you have primary current I1 and a secondary current, let us say I2, plus minus primary voltage, secondary voltage, number of turns N1, and this is N2, let us say. N1 greater than N2, step up, step down. N1 less than N2 is step up, isn't it? N1 is greater, then it is step down. N1 is less than N2, then it is a step up transformer, isn't it? So if you energize the transformer here in the primary winding, when you send some current through it by connecting an energy source across the primary terminals, then what will happen? What will happen here? There is some flux which is connecting only to a primary winding. Okay, and also some flux is also going to link with the secondary winding because of the current flowing through the primary winding. So this flux usually we call it phi 11, let us say, and this flux is, you call it phi 12. The flux linking with the secondary coil when the primary coil is energized or excited, isn't it? So because of that, what will happen here? Due to this flux, there is an EMF induced called self-induced EMF in the primary winding, and due to the flux linking with the secondary winding, because of the current flowing through the primary winding, that is phi 12, there is some EMF induced here. That EMF is called E2 dash. It is called mutually induced EMF. Okay, this is self-induced EMF, this is mutually induced EMF. And when you send the current, let us say, or energize the secondary winding, then obviously what will happen? It will have its own flux which will link with only the secondary coil, call it phi 2, and also some flux is, okay, linking with this particular coil, you call this particular flux, okay, as phi 1. What do you mean by phi 1 here? The flux linking with the primary coil due to energizing, or when you energize the secondary coil, what is the amount of flux that is linking with the primary coil? I hope you understand the point. But because of this particular flux, there is an EMF induced in the secondary, that is E2, and due to this phi 1, which is linking with the primary, there is an EMF called E1 dash. Now this is mutually induced EMF in the primary coil due to the current flowing through the secondary coil. I hope you understand it. V2 and I2 are related to what is secondary, and E2 is nothing but what here? What is E2 here? Self-induced EMF in the secondary coil. So I think you understand now. The total flux linking with the primary is nothing but what? Phi 1 plus phi 12. The total flux linking with the secondary coil is what? Phi 2, let us say phi 2 plus phi 1. The EMF induced in the primary total is what? E1, okay? That is total E1. E1 total, let us say, E1 total is nothing but E1 plus or minus E1 dash. Then EMF induced in the secondary total, E2 total, is nothing but E2 plus or minus E2 dash. Okay, so it's self and mutual together, algebraic sum together is nothing but the total EMF induced in the primary. Again, similarly here also, self and induced EMF in the secondary winding, algebraic sum is nothing but the total EMF induced in the secondary coil. Okay, but how do you know this plus or minus? Okay, whether it is a positive or negative. If it is positive, net EMF is increasing. Yes or no? When there is no mutual coupling, there was only one EMF called what? E1. You see the first category of the circuits, electrically coupled but magnetically separated. We have done so many problems on this particular category. So far, whatever the problems we have done, those problems, okay, are related to the first kind of circuits or first category of the circuits. Because there was no mutual induced EMF concept. There is no common flux concept. Understand all of you, okay? So, if you don't have any mutual coupling or the first type of circuits, you never have this particular component. Then E1 total is nothing but E1 only. But just because of the mutual coupling, okay, there is a common flux sharing between two coils. Now there is a component, additional component is coming to picture, there is mutually induced EMF, but who will really identify the sign of it or recognize the sign of or fix the sign of the mutually induced EMF? You understand all of it? Okay, self-induced EMF sign, we know how to find it. We have done so many cases where DC circuits, AC circuits, many of the cases. But now the sign of the mutually induced EMF is very important here to be identified. So those signs, okay, of mutually induced EMF can be determined using dot convention method. What is that method? Dot convention method. We will see the dot convention method a little later. Okay, we are going to explain that dot convention method. So this is how you can understand now electrically coupled but magnetically separated. We can give a simple example for this particular one. Okay, so these two inductors are or two coils are electrically coupled, but there is no mutual flux concept here. Understand? Okay. But second category is see, there is no physical contact between the two coils, but these two are magnetically coupled. There is a common flux sharing. Understand? Okay. Now this kind of category is that, okay, generally the representation of this particular one will be of like this. Okay. Now here the other category is Okay, between these two there is a common flux. Okay, otherwise you can say this kind of third category can also be shown like this. They are sharing common core. Understand all of you? Okay, so usually that dot convention method, I'm going to explain how the dots are created. Okay, but the dots indicate that they are mutually coupled. Okay, even if you do not indicate like this, but the dots, if you indicate, they are mutually coupled. Understand? So inductively coupled but electrically separated. Both inductively and conductively, because there is a physical contact as well as magnetic couple. Here also physical contact directly between the two coils and magnetic couple because of the dots. Now here the physical contact is there, but there is no common flux sharing concept here. There is no dot. Okay, therefore this is the first kind of circuit. The first, second and third. This is the first type of circuit. This is the second type of circuit. These two are third type of circuits. Understand all of it? Okay. So please note down quickly here all these things, and we will just move on to the dot convention. Quickly note down. Now let us see. Suppose if a single coil is excited. Say there is a single coil. So there is a current flowing to this one is I1 and the voltage applied is of V1. So the flux linking with the coil is going to be like phi1. Okay, there is no phi11, phi12 concept here because phi11, phi1 both are same. No phi12 because there is no non-magnetic core and no other coil involved in this, right? Say the number of turns of this particular one is n. Say the current flowing is I and this is V and N1, there is nothing but N, let us say. Now, you already know that according to Faraday's law of electromagnetic induction, E is directly proportional to, E is directly proportional to time rate of change of flux linking with the coil is equal to minus N d phi by dt. This negative sign is just because of Lenz's law, isn't it? Okay, what Lenz's law says? Cause opposes the effect, or effect is always opposed by the cause, let us say. Okay, cause and effect relationship, let us say. Okay, so who is the cause here? Who is the cause? Tell me all of you. Flux, let us say. Because of the flux, you get EMF. What is the EMF induced here? This is the EMF. So effect opposes the cause or cause opposed by the effect, whatever. You will get the negative sign here. Now, E is equal to N d phi by dt. You know that N into d by dt of phi by I into I can write. Yes or no, all of you? But you also know that if you take the relation between the flux and current, once the current is increased or increasing through the coil, then the flux will also increase linearly, okay, up to a certain point, and after that it will reach a saturation. This is called magnetic saturation. What do you call it? Magnetic saturation. We already learnt in the inductor case, okay, what is magnetic saturation. We discussed inductors topic. Yes or no, all of you? So you can see the slope of it. Now the slope will become phi by I. Now tell me, is it not constant here? Is it not constant? It's a constant. Therefore, d by dt of constant into I will give you n phi by I di of t by dt. That is I or I of t, both are same. Now this one can be replaced by L di by dt. Okay, where L is called self-inductance. What do you call it? Self-inductance. Understand all of you? Please note down. Now we will see when two coils are there, how it goes. Note down. Second case, let us take two coils, like what we have taken transformer. Okay, when the first coil is excited, then the flux is also linking with the secondary coil, some of the flux, and EMF is induced in the secondary coil due to the, according to Faraday's law of electromagnetic induction principle. Yes or no, all of you? So, according to that, I am just representing here this is a magnetically coupled but electrically separated. Say this is I1. This is open terminals here. Okay, the current flowing here is 0. And now you are exciting or energizing the primary. Okay, I1 of t and V1 of t. Obviously, it will deliver some flux. The flux is nothing but phi11. Let me draw it clearly once again. This is N1, N2, and now when the primary coil is excited, okay, but also linking some other amount of flux. Isn't it all of you okay? So this is phi11, the first one, and what about this phi12? Isn't it all of you? What is the total flux? Total flux is how much? Phi1 is equal to phi11 plus phi12. Understand all of you okay? What is the amount of flux that is linking with only secondary coil in terms of phi1? That you can express phi12 by phi1, nothing but K. What is K? Here is nothing but coefficient of coupling. What is it called? Coefficient of coupling or coupling coefficient. Understand all of you okay? Which can also be written as phi12 by phi11 plus phi12. I hope you understand this, right? Now, the point is, E1 is directly proportional to what? D phi1 by dt. Because what is the amount of flux linking with the primary coil? Totally phi1. Not only phi11, but also what? Phi12. So, totally how much amount of flux? Phi1 only. So, the EMF induced in the primary, that is nothing but self-induced EMF, is directly proportional to the time rate of change of flux, the total flux linking with the primary coil. So that's what you got here, right? So N1 d phi1 by dt, and finally according to that concept, N1 phi1 by I1, yes or no? Because you can multiply and divide by I1, and finally you got d I1 by dt, isn't it? So L1 d I1 by dt, where L1 is equal to N1 phi1 by I1. But now let us proceed with E2 dash. What is the E2 dash here? EMF induced in the secondary coil due to the current flowing through the primary coil. We call it mutually induced EMF. Understand? So now is equal to number of turns, that is direct. Okay, let me see here something like this. Let me write like this. E2 dash is directly proportional to what? D. What is the amount of flux linking with this? Only phi12 by dt is equal to, definitely number of turns of the secondary coil will come into picture, and d phi12 by dt. Again let us divide d phi12 by I1 into I1 by dt. Now I'll get N2 d of N2, what is this? Phi12 by I1 into what? di1 by dt. Now this is called M21 di1 by dt. We call it mutual inductance. Mutual inductance. What was it called? Self-inductance. Okay. When primary coil is excited, the flux produced by the primary coil is not only linking with the primary, but some of its flux developed by it is also linking with the secondary. Because of that, there is an EMF induced in the secondary coil. This phenomenon is called, okay, mutual induction. The parameter which is responsible for that mutual induction is called mutually induced or mutual inductance. Okay, the EMF induced is mutually induced EMF, but the parameter which is responsible for all this phenomenon is mutual inductance. I hope you understand the point. Okay, so this is how when the primary coil is excited but secondary coil is left open. Okay, now when I take secondary coil excited, now primary coil left open, let us see what will happen. Third case. Secondary coil excited, V2 of t. Current flowing through this one is I2 of t. There is some flux. What is that flux you call? Phi to 2. But this flux is also linking with what you call this one is phi to 1. And because of this flux, there is an EMF induced in the primary. Okay, that is called E1 dash. And because of this, E2. This is self, but this is mutual because of the mutual induction phenomenon. Okay, then obviously mutual inductance term will come into picture. Isn't it, all of you? Therefore, what you get here, E2 is directly proportional to d phi 2 by dt. What is phi 2? Phi 2 2 plus phi 2 1. The flux linking with the primary coil due to the excitation of the secondary coil. But whereas the M21 is nothing but it indicates the EMF induced in the secondary coil, due to the excitation of the primary coil. So you should observe that terminology clearly. Okay, phi 21 and M21 different. Okay, in case of M21, what is involved here? M21 is N2 phi 1 2 by I1. So in M21, you will get a term phi 1 2. Understand, all of you? Okay. So what is phi 1 2 actually here? The flux linking with the secondary when the primary is excited. Understand, all okay? But what is M21? The EMF induced in the secondary when the primary is excited. This is how you need to interpret the terminology very clearly. Okay, don't get confused in the terminology. And I also told you the ratio of phi to 1. How much amount of the flux is linking with the primary when the secondary is excited, when it is expressed as a percentage of phi 2. Okay, this is what you get. This is nothing but I told you already. What is this? Coupling coefficient. So phi to 1 by phi to 2 plus phi to 1. Understand? Now, if you keep that aside, E2 is directly proportional to d phi 2 by dt and N2 d phi 2 by dt. And once again, if you apply the concept called into I2 divided by I2, and phi 2 by I2 will be constant according to that relation between the flux and current we have just proven with the graph. Okay, so N2 phi 2 by I2, then di2 by dt. This is nothing but L2 di2 by dt. Now this is self-induced EMF. L2 is nothing but N2 phi 2 by I2. That's it. Similarly, what is E1 dash, Nana? E1 dash is directly proportional to d phi 2 1 by, because the flux developed by or delivered by the primary, some of its flux, okay, some amount of that total flux is also linking with the primary, that is nothing but phi 2 1. So d phi 2 by d phi 2 1 by dt and is equal to N1 d phi 2 1 by dt, and if you again divide and multiply with I2, N1 phi2 1 by I2 di2 by dt. Now this term is m12. This is di2 by dt. Now m12 is n1 phi2 1 by I2, the EMF induced in the primary coil due to the excitation of the secondary coil. I hope you understand the point. Okay. So this is how when primary coil is excited and secondary coil left over, when secondary coil excited and primary coil left over. When both the coils are excited, then you definitely expect self and mutual, self and mutual. Yes and all of you. Okay. So please quickly note down all these things. Fourth one is when both the coils are excited, isn't it? When both the coils are excited, what will happen? Here I1, here I2, here V2, here V1, then obviously, and then flux, right? Okay. So this is phi11, this is phi12, this is phi22, this is phi21, right? So because of all this, you will get E1 as well as E1 dash. Here also E2 and then E2 dash induced in both the coils here, right? Now I told you already the total EMF here. So E1 is what? L1 di1 by dt. And what is E1 dash? M21. Yeah, M12, right? So M12 di2 by dt. What is E2? L2 di2 by dt. What is E2 dash? M21 di1 by dt. That's it. Okay. So what is M12? What is M21? We know very well, right? So what is M12? What is M21 here? And what is the total EMF actually here? E1 is nothing but E1 plus or minus E1 dash. We decide the sign using dot convention. Yes or no? E2 dash. So let us also look at some important relationship between the mutual inductance and self-inductance. So what is actually M12, Nana? M12 is nothing but N1 okay d phi 1 2 by okay M12 is nothing but N1 phi 1 2 by I1, isn't it? Okay, M1 phi 2 by phi 2 1 by I2. What is M21? N2 phi 1 2 by I1, isn't it? If you take M12 into M21, then N1 phi 2 1 by I2 into N2 phi 1 2 by I1, isn't it? But you already know that N1, this is K times phi 2 by I2. Already you know that. What is phi 2 1? It is nothing but K times phi 2. N2 again K times what is it? Phi 1 by I1. You know that N1 phi 1 by I1 is nothing but L1. N2 phi 2 by I2 is nothing but L2. K into K square. So K square L1 L2. Understand all of you? Okay. And let M12, the property of mutual induction, that is the property which is responsible for the mutual induction process. Assume that same, okay? When primary is excited, whatever the mutual induction concept is taking place, that property, whatever you're taking, the parameter which is responsible for that particular property, let us assume that M12 is equal to M21, both the sides is same, means M. Then what will happen here? You will get M square. Yes or no, all of you? Okay. Then what is M? K times root L1 L2. Understand all of you? Okay. K is equal to M by root L1 L2. Please note down. So what is K actually? K is the coupling coefficient or coefficient of coupling. And it is the measure of magnetic coupling. Okay, so please note down quickly. Please note down. What is K? Coupling coefficient. It is a measure of magnetic coupling between two coils, right? Definitely magnetic coupling between two coils. And the K range is how much? Always between 0 to 1. Understand all of you? Okay, always between 0 to 1. That means K always belongs to 0 comma 1. That means it is between 0 to 1, including 0 and 1. So what will happen if K equal to 0? 0% linkage and 100% leakage. Yes or no? There is no flux at all linking with the other coil. Okay, 0% linkage or 100% leakage. K is equal to 0.1, let us say, 10% linkage and 90% leakage. K is equal to 1, 100% linkage and 0% leakage. This is how you can interpret with respect to K. Okay, so quickly note down all these things, all of you. Understood, all of you? Okay, so this is how you can interpret. K value is very, very important here. Coupling coefficient. It is a measure of magnetic coupling between the two coils. Understand, all of you? It will clearly indicate how much amount of or how much percentage of the total flux, okay, emanating from one coil and linking with the other coil. Now here you see 0% linkage. That means 0% is linking with the secondary coil. The flux emanating by the one coil, that primary coil, let us say, for example, then only 0% is emanating and linking with the other coil. Okay. Now 10% of the flux emanating from the primary coil is linking with the secondary coil. Understand, all of you? Okay. 10% of the flux emanating, the total flux, 10% of the total flux emanating from the primary coil is linking with the secondary coil. This is how you can interpret. Okay, so K value is very important. Sometimes you will mention only 50% of the total flux emanating from the primary coil is linking with the secondary coil. 50% means K is equal to 0.5. So like that you have to understand this, okay? So now let us see the dot convention clearly, okay? So what is dot convention? The dot convention, why we go for dot convention? It is to decide the sign of mutually induced EMF. We are well aware of self-induced EMF sign, how to indicate the sign, okay? I told you already before we had started this magnetic coupled circuits topic or chapter, whatever the problems we dealt with, okay, in case of inductors, capacitors, excited by the AC sinusoidal, okay, all those things come under electrically coupled but magnetically isolated. There was no concept like mutually induced EMF, only self-induced EMF. There we know how to indicate the sign of the self-induced EMF. So identifying the sign of the self-induced EMF is not a problem. What is the problem here? Mutually induced EMF. Okay, sign of the mutually induced EMF. Polarity of the mutually induced EMF. So let's see the dot convention here. Put the heading, dot convention. Put the heading, dot convention. According to the dot convention, I'll take two cases here. First, I will take the dots for granted. Then I'll tell you how the dots can be created. Okay, that I will tell later. First, let us see. Assume that the dots are given. Remember, the dotted terminal is assumed to be at higher potential. Okay, with respect to other terminal. With respect to other terminal. The dotted terminal is assumed to be at higher potential with respect to other terminal. So this terminal is assumed to be at higher with respect to this. This terminal is assumed to be at higher with respect to this. Understand all of you, okay? Well, now say the currents are flowing like this. I1 and this is I2. Okay? Now I can interpret like this. Current I1 is entering this coil at the dot. Current I2 is entering the coil at the dot. I hope you understand the terminology what I am using. The current I1 is entering the coil at dot. The current I2 is entering the coil at the dot. That means both the currents are entering at the dot. Yes or no, all of you? Both the currents are entering the coils at the dot. Now this is similar to when both the coils are leaving the coils, or when both the currents are leaving the coils at the dot. Both are same. Understand? Here, let me give you again. This current I1 is leaving this coil at the dot. Similarly, I2 is also leaving this coil at the dot. Understand? Both are treated as same cases, and for these two cases, you will get the same sign for the mutually induced EMF. Now the mutually induced EMF sign will be the sign of the mutually induced EMF. The sign of the mutually induced EMF is same as that of self-induced EMF. I hope you understand the point. This is very, very important. That means when you get self-induced EMF sign negative, then the mutually induced EMF sign is also negative. Positive, then it is also positive. Understand? That means E1 is equal to total. If it is minus E1, then it is also minus E1 dash. Or if it is plus E1, then it is also plus E1 dash. So what is happening? Even if it is minus, if you take common, addition is taking place. That means net EMF is increasing. Net EMF increased means what? Net flux already increased. If net flux doesn't increase, net EMF won't increase at all. Yes or no, all of you? Okay. So flux increased. Flux will increase only when both the flux are in the same direction. That means the phi11, understand? Okay, or phi1, whatever the E1 you are getting, that is nothing but what? Because of phi1. Okay. And what is that E1 dash you got? It is because of phi21. The flux emanating from the secondary coil linking with the primary coil. Understand, all of you? How much percentage it is actually emanating and linking with this? It is K times. Understand, all of you? How many times? K times phi2. We already proven that, right? So phi1 and this is phi21. Now the flux linking with the primary coil when the secondary coil is excited, let us say, okay, both the fluxes phi1 as well as phi21 are in the same direction. I hope you understand. Okay. Therefore, therefore, the net amount of flux is increasing. When both the flux are flowing in the same direction, they are supporting each other, they are aiding each other. That is why you call this case as flux aiding case. Okay, flux aiding case. Understand, all of you? Okay, why we call flux aiding case? Tell me, all of you. The sign of mutual is same as sign of self. Both the signs same, means the addition takes place. Addition takes place means EMF increases. EMF increase means already the flux had been increased. The flux was increased. Understand, all of you? Okay, flux increase means the flux which is linking with the two fluxes which are linking with the the primary coil or else secondary coil, let us say, are flowing in the same direction, supporting each other, aiding each other. That is why this case can be called as what? Flux aiding case. Understand, all of you? Okay. Now the second case you can take is of one current is entering the coil at the dot, the other current is leaving the coil in the secondary at the dot. So this is entering at, this is leaving at dot. This is same as first coil is entering, second coil is leaving, or else second coil is entering and the first coil is leaving. Understand, all of you? Okay. Now here, let us say the sign of mutually induced EMF is opposite to that of self-induced EMF. I hope you understand the point. Okay. So these are the two cases we can see here. Now E1 is nothing but, if it is minus E1 total, minus E1, if it will be plus E1 dash, or plus E1 then minus E1 dash. Okay. So we know how to identify the self-induced EMF while writing the mesh equations, definitely. Okay. While applying KVL, we know how to identify the self-induced EMF sign. We follow fall in voltage, negative, rise in voltage, positive concept. We did several problems in that. Okay. But mutually induced EMF sign, whether it is a plus or minus, it all depends on the dot convention. Understand, all of you? Okay. What is the dot actually here? Dotted terminal is assumed to be at higher potential with respect to the other terminal. Please have a note of it. Now let us see how the dots are created. Let me take a transformer, it's the best example to understand. You must be aware of Ampere's law, Faraday's law of electromagnetic induction principle, Lenz's law, right hand thumb rule, all these things to understand this concept. I think all of you know what is the Faraday's law of electromagnetic induction principle, what is an Ampere's law, okay, and what is the right hand thumb rule, what is Lenz's law. We are all aware of it, right? Yes or no? Okay. So therefore, let us see now. See, when you want to create the dots, you follow the step-by-step procedure. What is the step-by-step procedure? You see, first you select any one of the two coils. Okay, let me select primary. Got it, all of you? Now, select any one of the terminals of the primary coil, or select the terminal of the primary coil where the current enters and put a dot. I repeat once again, select any one of the coils, doesn't matter whether you take primary or secondary, doesn't matter. Let me select primary. Select the terminal of the coil where the current enters. Assume that now you are sending some current here, I1, by energizing this particular coil. Okay, to identify the terminal where the current enters, I just intentionally send some current and put a dot here. So this is what one dot you already got. Understand all of you? Okay. So this current is flowing like this and coming out, and finally again flowing like this. Again is flowing like this, coming out. So this is the entering, this is leaving terminal. Yes or no, all of you? So in the first coil, I'm identifying the entering terminal and putting a dot. In the secondary coil, I should identify leaving terminal and put a dot. That's the concept here. But to identify the terminal where the current leaves in the secondary, you should follow some procedure. Okay, what is the procedure? See, look at this. When you know the current here, you put a dot here. Yes or no, all of you? If you know the current flowing through this particular coil, then you can put a dot easily. I cannot assume again here, right? Only one assumption can be made. In the first case, I made an assumption, yes, some current is entering at this terminal. So I put a dot. I cannot assume here. I have to identify the terminal where the current leaves. For that, look at this. When current is entering, definitely when current is flowing through a particular coil, there is a flux developed or produced by it, and it will establish the flux around the coil according to Ampere's law. Any current carrying conductor will produce the flux, Ampere's law says. And that will be established around the conductor in the circular loops or about the conductor. Yes or no? But this is a coil, not a conductor. Okay. So here, that flux is, we already know that this is phi11. Now what is this? What is this? Phi12. Understand all of you? Okay. This is phi12. Good. So what is the direction of this particular phi12? I can identify only by using right hand thumb rule. Okay. First you ignore this. I'll tell you how the direction is coming. Current is flowing like this. Right hand thumb rule. Hold the coil. Stretch your fingers along with the current direction while holding the coil. And your thumb indicates the flux. Actually, right hand thumb rule for a conductor is different from a coil. Okay. For a conductor, straight conductor, okay, this is the current and this is the flux. The finger shows the flux about the conductor, but the thumb indicates what? The current and flux. But for a coil, because you're taking number of turns, okay, it is completely different. Now the finger shows the current, and the thumb shows the direction of the flux. Now here you can see, if you stretch the fingers and hold the coil, and now the thumb is indicating the flux direction. So what is the direction of the flux? Tell me all of you. Upward. Therefore, it's something like this, something like this, something like this. That's it. Got it, all of you? Now this flux is linking with what? Secondary coil. Okay. Some percent of the total flux emanating from the primary coil is now linking with the secondary, and there is some EMF induced here in the secondary coil. That we called it as what? Mutually induced EMF. The phenomenon was called as what? Mutual induction. That's all of you. Okay. Now there was some EMF induced here. What is this called? E2 dash. What about this one? What? E1. Yes or no, all of you? Okay. Now because of this E2, now my responsibility is to find the current flowing through this particular coil. Yes or no, all of you? But to identify the current flowing through this particular coil, to identify the terminal where the current leaves, I must know now the flux. The same right hand thumb rule I would like to use. What is the flux actually linking with this particular coil when it is excited, or else when you made that coil, okay, to produce the flux. Understand all of you, okay? Then based on that flux direction, you can identify the current direction. If you know current, you identify the flux direction. If you know the flux, you can identify the current direction. But for that, what I do is I deliberately, okay, close the switch here to make some current flow, because already some EMF is available here. If you can generate the flux in this particular coil, okay, again by sending the current internally, by closing the switch, some current flows here. Because of this current, now there is some amount of flux produced by this particular coil when you close the switch. I hope you understand the point. Okay. See, I intentionally did like this. I know the EMF. If I arrange a closed path across the secondary coil, some current flows. Because of that current, okay, some flux will be, definitely the flux will be produced by this particular coil. Understand all of you? Based on that flux direction, now I identify the current direction in the coil. I hope you understand the point. Okay. So now because of this current, some flux is produced according to Ampere's law. Any current carrying coil will produce a flux. But that flux produced in this particular coil will try to oppose the flux emanating from the primary coil. Agree all of you? According to which law? Lenz's law. So Lenz's law says this is the effect. This is the cause. Okay, the cause is what? The flux emanating from primary coil. So now the